We're going to start a chapter today on solubility equilibria. You'll see it very much fits in with what we talked about with chemical equilibrium as well as acid-base equilibria. So there'll be a tremendous number of similarities. Same big idea 6 that we've talked about quite a bit, and you'll especially see the effect of external perturbations on, in this case, solubility equilibria. So we talked about solubility earlier in the year, and we know that certain substances are always water soluble. For example, all nitrate containing compounds are water soluble, all group 1 containing compounds are water soluble, all ammonium containing compounds are water soluble. So we're going to be staying away from the soluble ones, and we're going to look at the ones that are barely soluble or slightly soluble. And we're going to represent that with a solubility product constant, KSP. K for constant, SP for solubility product. And this belongs to our entire KEQ family that we've talked about quite a bit this 9 weeks. Solubility product constant sounds much worse than it is. It says the product of the concentrations of the ions involved in a solubility equilibria, each raised to a power equal to its stoichiometric coefficient. KSP, like KEQ, like KA, like KB, like any capital K, not talking in regard necessarily to rate laws, that's something different, although that is temperature dependent as well. But KSP is temperature dependent. The only factor or stress that alters the value of KEQ, KA, KB, and now KSP is temperature. And that's a point that we have already made, and you want to make sure you've got mastered. The KSP expression is based on the balanced chemical equation. You'll always have 1 mole of a solid, and that solid is barely soluble. You're not looking at substances that are highly water soluble, like sodium chloride, like sodium sulfate, like group 1 anything, like ammonium sulfate, etc., or any nitrates. So for example, there are 6 sulfates that we consider insoluble in water or barely soluble, one of which is barium sulfate. Barium sulfate, the equilibrium would lie far to the left. The KSP value would be to a negative exponent. You'd have barium ion and sulfate ion. The KSP, or solubility product constant expression, is equal to the concentration of the first ion raised to its coefficient 1, concentration of the second ion raised to its coefficient of 1, and that KSP is equal to 1.1 times 10 to the negative 10 at 25 degrees Celsius. It is temperature dependent. There is a table of solubility product constants in your textbook. You can refer to it. Those pages are provided to you. Alternatively, I have several reference tables. If you'd rather I posted, I would be happy to do so. There it is. So here would be a table of KSP. For example, aluminum hydroxides. Most hydroxides are not water soluble or barely. And this one, KSP, is very, very small. Here are the barium-containing ones. Here's barium sulfate that we looked at, etc. You'll see barium nitrate, that is water-soluble, so the KSP value will be much greater. So the smaller the KSP, the less soluble it is.
Do we get that on the APC?
You would be given the KSP you needed. You wouldn't have to go off a table, but in your homework, they don't put it in every homework problem. You have a table in your book chapter as well as at the end of the book as well. There's a whole appendix there that I'm sure you've used already. And those page numbers are provided. Say it again?
The table is hard to find.
I know. I would put a little paper tab there so it's easily accessible. If you want me to throw them, you want them on Edline or Google Classroom? Edline. I can put a whole reference table tab in there, and maybe that'd be easier to just look at on your phone, etc. That's a good idea. All right. First example, it says write a solubility product constant expression for equilibrium in a saturated aqueous solution of the following slightly soluble salts. The first is iron 3 phosphate. Your approach here is you first write the chemical formula for the compound. You all know how to formula write inside out, but do you know your polyatomics yet? I certainly hope so. If not, that's something you want to brush up on before your next class. They're all in Quizlets and things like that. It's very easy to practice. Do 5-10 minutes from today until Wednesday and you'll be golden with it. Iron 3 phosphate, FePO4, generating iron 3 ion and phosphate ion. And again, equilibrium lies far to the left because these are barely soluble. So barely soluble means you're going to keep that as a solid, not as ions. The KSP expression is the concentration of the first ion, which is iron 3 ion, times, because it's the product of concentration of phosphate ion, each raised to the first power. Why don't you include the iron 3 phosphate? It's a solid, and you're always going to have that with KSP expression, so there's no denominator in a KSP expression. Okay? Let's do the second example together. You'll see that, and we can also use the table to find the values if that would be helpful to you. In the first example here, we've got chromium 3 hydroxide. And my approach here, and I think the approach is critically important, because some of you with a template can do problems pretty easily, but then you pull the template away and you're lost. It's like on the quiz, I don't know where to start. I know this, I know, and you just can't get it to click into place. That's a lack of practice, and you've got to be able to think about strategies that will get you where you need to go. So in regard to chromium 3 hydroxide, I don't just write my KSP expression right away. The first thing that I do is I write the chemical formula for chromium 3 hydroxide. That's chromium 3 ion and 3 hydroxide ions. Make sure you're balanced for charge. 3 pluses and 3 times 1 minus is 3 negatives for a net neutral. Now that is my equilibrium equation, but it's not my solubility constant expression. That's KSP is equal to the concentration of chromium 3 ion times the concentration of hydroxide ion raised to the third power. That is my KSP expression.
And then you wouldn't divide it by the chromium hydroxide because it's a solid?
Correct. And KSP expressions will never have a denominator in them. So that's a solid, not included. You are correct. The next one says aluminum carbonate. Give it a shot. What'd you get? What'd you get? You ready? You got an answer?
Does it matter the length of it? Because like you drew the equilibrium.
No.
arrows.
I just want you to know that equilibrium is far to the left. Yes, yes? Sure. Is that better? It's good? All right? Have to be able to do that. You get something so easy, you jump for joy and you keep going. And I've seen a lot of these very simple type questions in the short part 2s on the AP exam. And you'll see where it's going from here, but it's not difficult. There is a relationship between KSP and molar solubility, which we're going to call S. Molar solubility is S. And molar solubility will be equal to the concentration of the ion raised to the first power. And I'll show you what I mean there in a few minutes.
Why isn't it just equal then?
Why is it equal?
Why isn't it?
It is. Why isn't what equal?
Like, why do you need to put an exponent if it's just to the first power?
I want you to see first power, because molar solubility here is not equal to this concentration. It wouldn't be equal to this concentration. But if you look at this one, what concentration would the molar solubility S be equal to? The chromium 3 ion. That's why I put a 1. And you'll see the distinction in a few minutes. You can calculate KSP for molar solubility or vice versa, and we'll be taking a look at that. When we talk about KSP, we're talking about slightly soluble salts, not ones that readily dissolve because of problems with interionic interactions. Remember that if you have something like aluminum carbonate, which is barely water soluble, its interionic interactions will be stronger than the ion dipole forces that can form. In contrast, if you had something like sodium chloride, the ion dipole forces will be stronger than the initial interionic interactions. And we talked about that in a previous pre-lab. So we're only going to deal with slightly soluble salts here. So no group 1 containing compounds, no nitrate containing compounds, no ammonium containing compounds. We can calculate KSP from data, and that's shown here. And we'll look at this one, and then we'll walk through a fresh one. It says at 20 degrees Celsius, the saturated aqueous solution of silver carbonate contains 0.032 grams of silver carbonate per liter of solution. Calculate KSP. So to calculate KSP, we are going to need to figure out the concentration of silver ion, the concentration of carbonate ion. If we are not given either one, then the concentration of silver ion will be 2 times that of carbonate ion from your stoichiometric coefficients. So what they give us is 0.032 grams of silver carbonate. And from that, we can calculate how many moles of silver carbonate there is simply by dividing by the formula mass. And then we can calculate moles of silver ion, the 1 to 2 mole ratio, and moles of carbonate ion. This mole amount will be equal to this one because of the 1 to 1 mole ratio. Is it clear that silver ion has twice the quantity of carbonate ion? And then we're just going to divide each by 1 liter because it says per liter of solution. Once I have these two, I plug them in here. But why do I need to also square the concentration of silver ion? Coefficient of 2. And this bothers the kids. They feel like they're double dipping almost. They've doubled the concentration and then they square it. And that's okay. If concentrations of both are provided, don't make changes based on coefficients. Be careful there, and we'll point that out later. Plug in and solve. KSP is equal to this. Back in 2006, the first part of the first question is here. And it looks daunting, but I think as we work through it, you'll find it to be relatively straightforward. And as I said, you just hope you will see one of these. It says, answer the following questions that relate to solubility of salts of lead and barium. I'm only giving you the lead piece here. A saturated solution is prepared by adding excess lead-2 iodide to distilled water to form 1 liter of solution at 25 degrees Celsius. Concentration of lead-2 in the saturated solution is 1.3 times 10 to the negative 3 molar. Chemical equation for the dissolution. Dissolution, you're dissolving in water. It's not decomp because you're generating ions. With decomp, you don't generate ions. Be careful there. Lead-2 ion and 2 iodide ions. So that's given. And the first thing, it says write the equilibrium constant expression. Give it a shot. Try and just do little Roman numeral 1. And it says equilibrium constant expression, but you know you're writing a KSP, correct?
Yes.
How do you know? Because the reactant is a solid. If you threw in solid lead-2 iodide, would equilibrium shift? Why not? Because it is a solid and not included in the KSP expression, correct? That's something a lot of you are continuing to miss on your quizzes and tests. Did you get this? Yes, yes? Okay. The next question is to calculate the concentration of iodide ion. They tell you that the concentration of lead-2 ion is 1.3 times 10 to the negative 3 molar. And they want to know the concentration of iodide ion. I'm going to have to go a little bit littler. What are you going to do? Nah, it's really easy. Right. Just going to do a mole to mole ratio, or a molar to molar, if you will. This is lead-2 plus. From the balanced equation, you can do moles, molar, it doesn't matter, to 2 molar iodide because of the coefficient of 2 in the balanced equation, and you have 2.6 times 10 to the negative 3 molar. And then in part 3, it says calculate KSP. So what are you going to put in the place of lead-2 plus? That was given, good.
And then 2.6 times 10 to the negative third squared.
And don't forget to square. No unit for KSP. And that's at 25 degrees Celsius because it is temperature dependent.
Would any of the K's have units?
No. Because they're different depending on the equation. Like this one would be m to the third, and so it's too confusing. One other thing I do want to mention, because some of you without a calculator get so worried. 2.6 squared. 2 squared is 4. 3 squared is 9. So it's got to be somewhere between there. All right? So let's say you were at like 6 or 7. It doesn't really matter. And then you multiply by this. Now you're in about the 8 range. 10 to the negative third times 10 to the negative third, which is squared. 10 to the negative third squared is 10 to the negative 6 times 10 to the negative third. Add those exponents. So make sure you can do some of it in your head.
On my calculator, like, it doesn't go all the way out. It just rounds it to 9.
That's all right.
So,
You'll be fine. Because in a multiple choice type thing, it's fine.
so there won't be like, this is a part 2 though. Like, what if?
Yeah, some of the calculators you can set into scientific notation, but you'll be within the range. You'll be okay. All right? Pretty straightforward. What is S? Not asked for, but I want to make this clear because you're going to need it in the next section. What is S equal to? You got it. So that is the molar solubility of lead 2 iodide.
Why is that?
Why is what?
Why, what?
Because S is always equal to the concentration of the ion to what power? 1. And that's why I put the 1 there, because you have to see it. It is not equal to this.
What if both of them have coefficients?
Then you're good. Oh, if they both have coefficients, if they, I would go after the one that had a coefficient of 2, see what that concentration is, and divide it by 2.
Okay, and then if neither of them do, but the concentrations are different, then
I'd still go after that one. If you, because you're either going to have, you only can have so many combinations, and I'll show you that in just a sec, but you either have like a 1-2, a 1-3, or a 2-3, and that's as much as you're going to have. So you can always find either something to the first or something to the second and divide by 2.
what if you have 1, 1, and they're different though?
No, they, one of them they will tell you is the molar solubility. The other one will be provided to you, and you'll see that in a little bit afterwards.
Same anyway if they were.
No, but see, there can be situations where, for example, KSP is given and something is to the first power and it's given, but it's not the molar solubility, so there are variations there. We'll get there. Yeah, that's a good question. We'll get there. All right, the other thing I want you to see today, and this is easy as well, it says calculate equilibrium concentrations and or the molar solubility of a solute from a tabulated KSP. And what that means in English is that KSP will be given and you want to find S. So you're just going the other way. We'll take a look at this first problem, we'll walk through the next one, and with a little practice you will have mastery. Those of you who went crazy practicing for the quiz and texted me all weekend with a lot of questions, you look like you know what you're doing. Those of you who didn't do enough practice, you were just all convoluted there. This one says calculate the molar solubility S of silver arsenate. Arsenate AsO4 3- doesn't have to be given, you should know it. KSP is 1 times 10 to the negative 22. My approach here would be to write that equilibrium equation, balanced equation. KSP, you know how to write the expression. Note I highlighted the one in red because the concentration of arsenate ion is equal to what? S. All right, here's where it gets a little funky, and it's going to be a little bit bothersome to you initially, but I think you'll grasp it. We established in the previous problem that the concentration of iodide ion was twice that of lead 2 ion. And so essentially, we also said that this is the same as S, and you can see here that this is 2S in here, correct? Now you're going to see it here. So silver ion raised to the 3rd power, so the concentration of silver ion is 3S. It's 3 times the concentration of arsenate ion, which is S. Where you need to be careful is put how many S's you have in parentheses and then apply the exponent, because this is not 3S cubed. It's not 3S cubed, it's 27S cubed times S is 27S to the 4th power. KSP was given. You want to solve for S. My approach to solve for S would be the following in the calculator. I would do 1 EE negative 22 divided by 27 equals, and then I would take that to the 1/4 power. Arrow up, open parentheses, 1 divided by 4, or you could do to the 0.25, close, and S is equal to 1.4 times 10 to the negative 6. Now S is equal to the concentration of arsenate ion, and why is the concentration of arsenate ion here equal to the concentration of silver arsenate? 1-to-1 mole ratio. So this is a little bit funky in that, and this bothers the kids. They're like, well, you triple it and then you cube it also, but you do. S. Concentration of the ion to the 1st power. Let's do one from scratch, and I think you'll have some basis for it, but until you practice it, you will not have mastery. It says calculate the molar solubility. So we're looking for S. For silver chromate, and KSP is equal to 1.2 times 10 to the negative 12. Now silver chromate two silver ion, 1 chromate ion. So my KSP expression would be what times what? Silver ion to the 2nd, chromate ion to the 1st. So S will be equal to the concentration of chromate ion. All right. So we have 1.2 times 10 to the negative 12 is equal to, what am I going to replace silver ion with? 2S squared. And this will be? So that will be 4S to the 3rd. Well, I'm just thinking, this is one of those that you could do without a calculator. If you divided both sides by 4, you're going to cringe. It's going to be 0.3 times 10 to the negative 12 is equal to S to the 3rd, right? And then if you take all of this to the 1/3 power, actually I don't think, if you had 27 times 10 to the negative 12, you could do it. This you probably would fall a little flat on. But you have 0.3 EE negative 12, arrow up, 1 divided by 3. And so S is equal to 6.7 times 10 to the negative 5, and that's molar, equal to the concentration of chromate ion. And so that will be equal to the concentration of silver chromate. Questions there? I do want to show you that there are only certain relationships that you will get. I think it will be helpful to you. For example, if you had silver chloride, KSP would be equal to silver ion times chloride ion, so that would be S squared. If you had silver chromate, KSP would be equal to silver ion squared, chromate ion, we just did this one, and that would be 4s to the third. If you had chromium hydroxide, which we looked at the beginning, you would have chromium 3 ion. So chromium 3 hydroxide, you have chromium 3 ion, hydroxide ion to the third, and that's going to be 27s to the fourth. And you also can get 108s to the fifth. So there are only certain combinations that you can have. And that's why I said you've got S's, you've got an S, you've got an S, and only if you had a 2, 3 would you have to divide it out.
Where did you get the 2? No, I got it.
You got it?
Yes.
So you only have certain combinations, and that'll lead into the next problem, but we're going to pick up with that when we return. At this point, you want to know what a KSP expression is, know how to write it, and know how to solve it. And we'll continue with this, and there'll be a lot of review concepts from what we've talked about with chemical equilibrium and for acid-base equilibria as well.